So I just wanted to take a step back and talk, kind of give you a bigger picture of why we are talking about or care about soups or imps. One of the big reasons we care about a soup or an imp is that every bounded set must have a soup or an imp. So if I have a statement that I have to prove, like if A in R is bounded, then whatever I have to prove. That's not much information, but I do know that A must have a soup, and it must have an imp, and I have some definitions to work with then, something to get my hands on. And so that's one reason, one big reason that we use soups and imps. And then the next question I think might be on people's mind is, why do we need these weird definitions? Isn't soup of A just kind of like a max? Well, no, because the max of A must be attained in the set. Not all bounded sets have a max, so I'm going to show you in a second an example, draw out an example, 1 minus 1 over n. That has no max because the max is not attained. The max, if it was a max, it would be 1, but it's not in the set. 1 is not in the set. So therefore, we must go to the soup. And it's in real analysis, we care about soups and imps. So it's actually baby real analysis we care about it, but we really have to know what this is in the graduate real analysis course as well. So there's a lot of results that you're going to prove that are about limits, and they may seem intuitive, but actually getting down and proving it means that you have to work with something. I'm going to prove in here a well-known theorem called the Bolzano-Weierstrass Theorem. I love all the Weierstrass theorems that are out there, so I could pick this one because I really like it. But the statement says that every bounded sequence of real numbers must have a convergent subsequence. If it's already convergent, this is an easy proof, but there are bounded sequences that are not convergent. So what I have here is that if A is xn, the sequence, it's bounded, then there exists an xnk, that's a subsequence, such that that limit exists, and this x actually is a number. So this is what I'd have to prove and draw out. Well, since I know A is bounded, I know it has a soup and an imp. Let me give you an example to illustrate this. Here's a bounded sequence that doesn't converge, minus 1, 1, minus 1, so it's a flipper. I can see what the A convergent subsequence is. I just have to show the existence of 1. So all 1s is a convergent subsequence, which happens to also be the soup. So it leads me to believe that I can always find a subsequence that converges to the soup. So anytime I prove there exists, this is important because anytime I have to prove there exists, it's good to have a candidate for what I'm looking for. So my candidate, just looking at this one example, for a limit is the soup of A. So now I have to show that there is actually elements in the set that generate a subsequence that converges to the soup of A. Seems like it should work. And that's actually the plan for Bolzano-Weierstrass. But you have to know what a soup is, and you have to know what an inf is very well to understand that proof. And some of you asked for harder proofs. That's a harder proof. But it's a good educational proof, but I don't want to take you there if it's going to be me going wah, 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 wah all class long.